Hello everyone, and welcome to AISC's live webinar, New Composite Design Provisions in the 2010 Specification. Today's webinar is being presented by Will Jacobs of Stanley D. Lindsay and Associates. My name is Brent Liu, and I am with AISC's Continuing Education Group, and I will be moderating today's presentation. I want to introduce today's speaker, William P. Jacobs V, PE and SE. Will Jacobs received his Bachelor of Science degree from Clemson University and his Master's degree from Virginia Tech. He currently serves as an associate at Stanley D. Lindsay and Associates in Atlanta, Georgia, where he has been involved in the design of building structures throughout the Southeast. He's a registered professional engineer in Georgia and South Carolina as well. He's a registered structural engineer in the state of Illinois. Mr. Jacobs is Vice Chair of AISC's Task Committee 5 on Composite Construction, which guided the development of Chapter I for the 2010 AISC Specification. He is also the primary author of the Composite Construction Design Examples for the 14th edition Steel Construction Manual. Additionally, he serves as a corresponding member of AISC's Task Committee on Seismic Design. He is a member of AISCE's Composite Construction and Methods of Design Committees, a member of AISC's National Technical Planning Committee for Structures Congress, an associate member of AISCE 37, Design Loads on Structures During Construction. I want to welcome you, Will Jacobs. Appreciate you being here today, and I'm going to hand things over to you.
Thank you very much, Brent. Good afternoon, or morning as the case may be. Again, my name is Will Jacobs with Stanley D. Lindsay and Associates in Atlanta, and today I'm going to be talking about the new composite design provisions in the 2010 AISC specification. Now, I've broken the talk down into two parts. In part one, I'm going to discuss the revisions that have been made to the specification itself, and then in part two, I'm going to review the composite design examples that were created to accompany the 14th edition Steel Construction Manual. Before I jump into the main part of the presentation, I want to take just a minute to review a topic which seems to come up a good bit in various engineering circles, and that is the topic of the code cycle, primarily the pace at which various specifications are being released and their expansion, both in terms of complexity and number of provisions. And I'm going to try to address this topic by sort of giving you my take on the previous code cycle. So it went like this. I received the 2006 International Building Code, which is a big 5-inch thick 3-ring binder, and seeing this, I decided I should probably also get the code and commentary. Given that the previous version only came out 3 years prior, I also received the significant changes to the International Building Code. And just in case I wanted to delve in a little further, I went ahead and purchased the study companion to the International Building Code. And for those engineers who really don't like to read in the first place, well, that's no problem because you can also get the illustrated 2006 IBC. So once you read approximately 3,000 pages of information in your spare time, if you're anything like me, you realize that this document basically says to see AISCE 705. So you pick that up, and let's say you don't understand some of those provisions. Well, that's no problem, because you can also purchase the guide to the wind load provisions, the guide to the snow load provisions, and the guide to the seismic provisions. Now, once you've assimilated approximately 5,000 pages worth of information, guess what? AISCE 710 comes out. And judging from my scientific survey of the thickness of AISCE 710, it appears to be equal to approximately 4 788 stacked on top of one another. Okay, so what's the point? Why am I talking about this in an AISC seminar? Well, I guess the point is I get it. I'm a design engineer just like many of you, and there are actually a lot of design engineers that help make up these committees that develop the AISC specification. So AISC as an organization gets it as well. And that's why in 2005, when we were first starting to work on the 2010 specification, AISC handed down a mandate of minimal change. They wanted the committees to only revise what really needed to be revised. Also, AISC has moved to a 6-year code cycle, so the next specification will not be coming out until 2016. So we're all engineers here. Presumably that means we like numbers. So what I want to do is I want to sort of give the composite committee a grade to see how well they did in meeting this mandate of minimal change between the 2005 and 2010 specifications by looking at the numbers. So in 2005, there were 5 main sections to Chapter I, and in 2010, there were 9. In 2005, we had 12 specification pages. 2010, not so good. Doubled it, 24 specification pages. So in order to explain why the number of specification pages went from 12 to 24, it makes sense that the number of commentary pages also had to increase, in this case from 22 up to 39. And then in order to illustrate the application of all these provisions, the number of design example pages increased from 28 up to a whopping 114. So I guess based on the numerical evidence at hand, the grade you would give the composite committee is approximately an F. But I'm actually here to say that the mandate was met because the mandate was minimal change, and your standard composite beam designs have not changed. The strengths for shear studs within composite deck have not changed. What has happened is that the provisions have been expanded beyond the use of composite beams to address composite columns more thoroughly, load transfer, detailing provisions, things of that nature. We've also clarified the existing provisions for ease of use and provided a good bit of additional guidance for designers, primarily within these design examples. So again, the substance of the existing provisions was really not modified to any great extent. Just sort of on a personal note about how I got into this business. Several years ago I was designing this building, which was a steel office building that went up and over a concrete television studio below that of course I couldn't place any columns in. So what we ended up doing was using 22-foot deep by approximately 130-foot long transfer trusses. And these trusses, where they came over and intersected the concrete below, we used a lift of composite columns, shown right here. Now when I was designing these composite columns, I had to determine what the shear strength was for these studs, the various transverse tie configurations, and there actually wasn't a lot of guidance given within the previous specification when it came to those topics. So I started asking some questions, and one thing led to another, and now 8 years later I'm giving a presentation on it. But I'm happy to say that due to the hard work of the remainder of the composite committee, along with the AISC staff, the 2010 specification addresses all of these questions very nicely. So this is what we've done. Chapter I has been reorganized. Concrete and steel reinforcement provisions are now handled primarily by reference to ACI 318, which I'll discuss in a minute. We've added local buckling provisions for concrete-filled tubes. We've expanded and clarified the load transfer provisions within the specification. All of the shear provisions have been consolidated into one new section. We've added a new section on composite diaphragm and collector beam strengths, and then we've added new provisions for shear studs. Now these provisions are not for your standard shear studs in flexural beam members. They are for load transfer provisions, as in composite columns. And I said the term shear stud. That's actually no longer correct because in 2010, the term shear stud has been replaced by the more generic and, in my personal opinion, boring term steel anchor. This was done to maintain consistency with ACI 318 Appendix D and other documents. You will probably hear me say shear stud about 50 times through the rest of this presentation. Just replace that in your mind with steel anchor and you will be compliant with the 2010 specification. So as far as a rundown of the reorganization goes, in 2010 the first three sections are the same as they were: general provisions, axial force, and flexure. Then we have this new section, I-4 on shear, combined forces in I-5, and new sections, I-6 on load transfer, I-7 on composite diaphragms, and I-8 on steel anchors. So what I'm going to do for the remainder of part one of the presentation is go through each of these different sections and highlight the revisions that were made and how this might affect your day-to-day design. So starting with I-1, general provisions. In 2005, there were sort of a hodgepodge of references to different reinforcing and concrete detailing provisions. We gave some of what you needed within the AISC specification, but not all of it. So rather than having this mix, what we did was anything that's not specifically related to composite members is just referenced to ACI 318. And then composite-specific provisions for rebar detailing are still referenced in the 2010 specification. Also, we added local buckling classifications for concrete filled members. In 2005, if you wanted to design a concrete filled tube as a column, it had to be a compact member. There was no other option. So in 2010, what we've done is added these tables that are very similar to the tables in Chapter B that will allow you to design non-compact and slender sections for filled composite members. Just to give you an idea of what the numbers in here might represent, if we take a look at the round HSS, the round HSS transition between compact and non-compact is about 100 for 42 KSI steel. That's the diameter to thickness ratio. And then the maximum permitted is all the way up around 200. So this would translate in the real world to, if you had a 30-inch diameter tube, you could use a wall thickness all the way down to about 3/16 of an inch thick. So very slender elements are now covered by the specification. So this takes us to section I-2 on axial force. And the first thing that was done in axial force is to implement the steel-only fix. And what I mean by that is in the 2005 specification, people noticed that if you had a stocky tube member and you filled it with concrete, you could actually calculate the compressive strength to be lower for the composite member than the member prior to you filling it with concrete. This obviously makes no physical sense, and that was not the intent. The reason that this happens is due to the difference in resistance factors between non-composite and composite design. For non-composite columns, you're using a phi factor of 0.7 or 0.9. For composite design, you're using a phi factor of 0.75. So when you have a thick-walled member that is dominated by the steel strength, the addition of that little bit of concrete was not enough to overcome the difference in the two phi factors. So that was fixed in 2010. A sentence was added that just says the strength need not be less than that of the non-composite member. This is also addressed within the 14th edition steel manual, where all the tables for filled members in compression have a line within them that delineates the difference between the non-composite member strength controlling and the composite strength controlling. So I've already thrown out a couple of terms at you. Let's clarify some things really quick. On the left, this is a filled composite member, also known as a concrete filled tube, or CFT, and that's just an HSS or built-up box shape filled with concrete. On the right side, we have an encased composite member, or SRC, which is a steel reinforced concrete column, and this is just a reinforced column that happens to have a steel section within it. And we're going to take a look at how you determine the axial strength of both these members in turn. We'll start off with the encased composite member on the right. So the strength is the same as it was in 2005. The only thing that we did was to clarify that local buckling effects for the embedded member did not need to be taken into account. Due to the confinement of the concrete, even if you have a slender web for your member, you can still assume that it can develop its full plastic capacity. The compressive strength is based on a plastic strength model. P sub NO is the cross-section strength, and that's just equal to the plastic strength of the embedded steel member, given here by F sub Y A sub S, and then the remainder of the terms is the reinforcing steel, and 0.85 F prime C, A sub C, is the strength of the concrete. Now that's just the section strength, and then we also handle slenderness effects, very similar to how they're handled for non-composite members. We just use a modified EI, which is the EI of the steel section plus a portion of the EI of the concrete section. And this is actually something that's being reviewed right now with some additional research to try to make this equation even better in 2016. We'll talk about that in just a little bit. There are also some detailing limitations for encased columns. The minimum ratio of encased shape to gross area is 1%, and then the minimum longitudinal reinforcement ratio is 0.4%. Now you may notice this 0.4% is actually lower than the 1% minimum for longitudinal reinforcement in ACI 318, and that's just because we're recognizing here that you also have an encased shape within the member, so your minimum total is still around 1.4%. In reality, studies have shown that somewhere in the range of 8 to 12% for the ratio of encased shape is the sweet spot for economy for members that are just resisting gravity loads. And then we have perhaps my favorite change that was made to the entire 2010 specification, and that has to do with transverse ties. And it goes like this. In 2005, we had a provision that said the minimum transverse reinforcement shall be at least 0.009 inches squared per inch of tie spacing. Now the only problem with this provision is that nobody knows what that means. 0.009 inches squared per inch. It's not intuitive. If you actually took a look and you interpreted that correctly, what you would find was that that equates to about a number 3 bar at 12 inches. So guess what the 2010 specification says? Use a number 3 bar or 12 inches. All right? You can tell that there are actually some design engineers on the committee now. So we tried to clarify some things. We also refer to ACI 318 for the support of longitudinal rebar. ACI 318 requires that if you have a bar that's more than 6 inches clear from another laterally supported bar that you tie it off. This is fairly easy to do with a reinforced concrete column, but when you have a steel section in the middle, it gets a little tricky. One way that this is possible is to use a diamond tie, such as what's shown on the left. However, there is some problem in doing this in that if you have steel members, steel beams coming in at the XX and YY axes of this composite column that interfere with that longitudinal reinforcement. So really the best way to handle composite columns is to try to bundle the rebar in the corners as much as possible. That comes with its own set of issues with increased lap lengths and things like that, but it does leave the middle of the column open to receiving other members. If that's not a problem, there are also some other things that you can do. If you have a large embedded shape, you can use weldable rebar to put ties directly to the flange as shown at the top and bottom here. You can also use something called carry bars or longitudinal restraining bars, which is just a number 7 bar up tight against the web that has a J-tie that goes out beyond the spalling plane over to hook around the longitudinal rebar. So that's another option. You can do a third thing as well, and that is to use 2-piece U-ties. This diagram is actually showing holes drilled within the structural steel member. To put these U-ties in, from personal experience, that is not a good idea. Contractors do not like to do that, but it's an option if you absolutely have to do something. And then you get into some messy situations as shown here. I guess the takeaway from this whole little discussion is to pay attention to the layout of your rebar. Try to bundle it in the corner if possible. If not, you need to see how you're going to tie that rebar off to meet these lateral support provisions. So that takes us through axial for encased columns. Now we need to look at filled columns. And like I said at the beginning, there's now this new concept of local buckling effects for concrete filled tubes. So we start off, we have a compact section. If the section is compact, then you determine the strength capacity using a plastic model, very similar to the encased section where you have F sub y, A sub s as your steel portion, and then a concrete portion that is multiplied by this C sub 2 confinement factor. And that factor varies anywhere from 0.85 for rectangular or square sections, all the way up to 0.95 for circular sections. And that just recognizes the increased confinement that that circular section provides for the concrete. And then you have this new concept of a non-compact section. Now for those of you who are very familiar with designing non-composite columns, this is a term that you don't see because your section is either slender or it's not. So when I say non-compact section, what I mean here is a compositely non-compact section. So what this is your steel casing is still able to develop the full plastic strength of the steel section. However, it's no longer able to provide the confinement necessary to prevent the internal concrete from starting to dilate a little bit. So it can no longer provide that 0.85 or 0.95 confinement factor. So the equation for a non-composite section is just F sub y, A sub s, plus now you have a 0.7, a reduced confinement factor. And then the third type of section is a slender section. And in this section, your steel can no longer develop its full plastic capacity. It now can buckle. And so you have a similar equation. You just use a buckling term, F sub cr, instead of S sub y. Now, if you plot these, shows like this. You've got your compact section, transition down, and your slender section all the way out to the maximum D over T or B over T values within the specification. So that takes us quickly through the axial force section. Now we'll move on to I3 on flexure. And again, for flexural strength of beams, there has been no substantial revisions. I know that composite design for most people means the design of composite beams, and so we are going to discuss that a good bit in part 2 of the presentation on the design examples. But we really didn't change a whole lot within the specification. Weren't able to contain ourselves completely though, so there were a few couple of tweaks here and there. The first thing that was done was the composite beam equations for you to design composite beams by hand have been added back. Those were removed from the commentary in 2005, and much to our surprise, people actually read the commentary and requested that they be added back. So they are back by popular demand. The second thing that was done is a edge distance has been added. Minimum free edge distance between the last stud on a beam and the edge of 8 inches in normal weight concrete and 10 inches in lightweight concrete. This will actually not come into play for most designs, and the reason is because it is a free edge. So for instance, if you have a girder, such as shown on the screen, this is not a free edge. You have a column that's going to keep the concrete from breaking out between this last row of studs and the edge of the building. And even if this was just a regular steel member, you most likely have a bent plate along the edge of the building that you can also use your engineering judgment to say will prevent that concrete from breaking out. So this is really only applicable to formed edges, probably not going to happen a lot within your standard designs. So let's take a look at the flexural capacity of filled tubes. Again, we have local buckling effect issues that are now handled very, very similar to how we handled the issues within the axial strength calculations. If you look in the new commentary, you'll see diagrams as shown on the top of this slide that give for compact, non-compact, and slender members the steel stress pattern and the resultant forces that are going to occur. And then within the design examples, you've got tables, such as shown on the bottom of this slide, that give the actual force equations and moment arms that you need to use to calculate these capacities. So for a compact section, it's the same idea as before. You get your full F sub y across the steel, and you can develop your 0.85 F prime C in the concrete. For your non-compact section, now we're down at 0.7 F prime C for the concrete stress. And then for slender, again, similar idea. You've got F subcritical now as your steel stress, still at 0.7 for your concrete stress. So if we want to plot that, it looks very similar to the axial section, in which you have a compact zone, a transition area, and then slender member out to the maximum B over T or D over T limits. Okay, so that takes us through that section. We'll now move on to section I-4, shear design. Really all that was done in I-4 is all the different member types were collected into one place within the specification. And there are now 3 different methods provided for design, but you will most likely only use one of them. And that is to simply ignore all of the reinforced concrete and calculate the shear strength of the embedded steel member. This will get you the capacity that you need in most all of your designs. However, if you would like to use another method, the second allowable method is to just ignore the steel member and take into account the reinforced concrete using ACI 318 provisions. And then we also allow a third method, which is sort of a combination of the two, where you take the structural steel member and the ties together, but you have to use a reduced phi factor of 0.75 to reflect the increased variability for this condition. It would make a lot of sense for us to come up with a method that would combine the full reinforced concrete section and embedded steel section, but we just don't have the data right now, so perhaps that might come in the future. That takes us through the shear provisions. We are now going to take a look at section I-5 on combined flexure and axial force. And there are quite a number of methods to check combined flexure and axial force within the specification. The first method is strain compatibility, which is just like concrete. I'm not really going to review that method today. But then there are 4 different plastic stress distribution methods that I am going to go over. And with each of these methods, there are some that are more difficult than others. The more effort you put into it, the more capacity you're going to get out of your member. So the easiest and probably most conservative method is just to use the Chapter H interaction equations, the same way that you would do with a non-composite column. This is actually a really good method for concrete filled tubes because you can get the axial strength and the flexural strength directly from the tables within the 14th edition steel manual. So you can go right in there, pick out your P, pick out your M, and plug them into these equations. One word of caution, in the 13th edition steel manual, in the black steel manual, they had the same tables for concrete filled tubes or axial force, but the capacity, the flexural capacity given at the bottom of those tables was the non-composite capacity of the member. It did not take into account the concrete in the 13th edition manual. In the 14th edition manual, those numbers have been updated to take the concrete into account. So just a word of caution there. If you'd like to put in this is the diagram, your standard bilinear interaction equation, Chapter H. Okay, so method 2, if you'd like to put in a little more effort, you can use a piecewise linear interaction curve. And what this is just using different anchor points to create a piecewise linear curve that mimics the strain compatibility curve. And these anchor points are provided directly within the design example with equations like what's shown on the screen here for the different member types. So you can directly calculate points A, B, C, and D. And if you take a look at the diagram that you get once you move all the way through this method compared to the Method 1 Chapter H interaction, you'll see that you actually do get a good bit more additional capacity out in this region. Now you really need to be careful if you're down close to this point D prime prime. It's possible to get an unconservative design, and I will sort of talk about how that might happen by developing one of these curves. So you start out here with your A, B, C, D curve on the outside. That's your curve without length effects. And then you apply a member slenderness provision to reduce this curve to A prime, B prime, C prime, D prime. And then you can apply your phi factor or your safety factor to get to your LRFD design or your ASD design. And if you look down at the corner of the LRFD design, you can see that there's a teeny little red section where the LRFD design equation was actually pushed out beyond the section strength. So if by some miracle you're within this teeny little red section, your design would be considered unsafe. Now this is for a specific column, so there are other columns that might have larger unsafe sections. So just note that if you're really pushing the limits of your design, you need to be a little careful about this. And one way that we can avoid this entirely is to use method 3, which is referred to as the simplified method in the commentary. And that is just to remove point D altogether. Just get rid of it. So your simplified method 2 is now a straight line from B to C over to A. This serves two functions. First of all, you get rid of this possible zone of unsafe action. And you can also use a nice and tidy bilinear interaction equation, as shown here. Now, these are provided directly within the commentary. Now, your final, fourth method is to use AISC Design Guide 6. Now, Design Guide 6 is fairly old. It's based on the 86 LRFD method. However, it is still safe, and you are welcome to use it if you wish. Now, a question that I ask a good bit is, where did all this come from? And generally the answer is mechanics-based formulations that are supplemented by numerical modeling that have been validated by research. And there's been some recent research into exactly what EI effective should be used for these columns. There's been a good bit of testing done at the MAST facility at the University of Minnesota. For those of you who are not familiar with the MAST facility, it is really neat. They have a giant crosshead capable of 6 degrees of freedom that can apply 1.3 million pounds of downward force at the same time that they're applying 900,000 pounds of lateral force. This research was done under an NSF grant by Georgia Tech and the University of Illinois at Urbana-Champaign. And what they did was test a range of composite filled tubes from 5 inches to 20 inches wide, all the way up to 26 feet tall. So what I'm going to do now is I'm going to show a little video of one of these tests. This is a stop motion video, so you'll see some lights flashing. And what's happening here is there is a uniaxial flexure back and forth during the first part of the video. And then they move to a figure 8 pattern of force application toward the second portion of the video. So they were getting a lot of data on biaxial flexure, uniaxial flexure, and the capacities of these columns. They're still sifting through all of this data, but it looks like the preliminary results is that the specification equations are pretty good. They can be tightened up a little bit for some very slender members. However, it's a pretty good representation of what's happening right now. So this just goes to show that we are actively engaged in research. There's a lot of research going on in composite design right now. Okay, so that moves us on to section I6 on load transfer. Now for those of you who don't know what load transfer is, the specification now guides you through it in 4 steps that correspond to the 4 sections in the specification. We're going to take a look at this encased column on the right to try to explain it, and we'll remove the encasement to give us an idea of what's going on in there. And step 1 is simply force introduction. And force introduction is where is your external force being applied to the composite column. Is it in the steel? Is it in the concrete? Or is it going to both? So once you apply the force, if you want this member to act compositely, then obviously the concrete and the steel both need to contribute. So you need to determine how much force each of the 2 different materials contributes to the total section strength. So in order for the force to get from where it was applied out into the remainder of the member, you have to transfer it between the 2 materials, and that's force transfer, I6.3, and then there are a slew of detailing provisions. So I'm going to hit each of these in turn, starting with number 1, force introduction. So again, force introduction is just how the external force is applied. On the left side of the screen, you have an encased column with a steel plate sticking out beyond, a extended tab plate. So this force is coming in through the tab plate. You could probably say that all of this force is coming into the steel section only. Conversely, on the right side of the screen is a composite column where almost all of the force is coming in from concrete beams and columns above. So you can say that all of it is coming in through the concrete. And then you have the general occurrence in real world where you have force that's sort of being applied to both materials at once. So once you determine exactly how your external force is applied, then you need to allocate it between the 2 different materials. And the way the specification puts it is this entire paragraph, but what this means in real world is you're just looking at ratios between the plastic strength of the steel or concrete and the overall section strength. So it's just a ratio game. When I mention this, if you look at the encased composite columns, your total section strength is given by, again, this plastic capacity model. So the first part of this is A sub S, F sub Y, and then the second part of this is your concrete strength. All right? So those are the 2 different pieces of materials that we're looking at for this model. So in order to see what I mean by a ratio game, if we take an example where we have a column and we're putting all the load onto just the steel section, and we calculate that ASFY, the plastic strength of the steel section, is equivalent to 67% of the total section strength. If we apply 100 kips to just the steel column, what we're saying here is that 67 kips are going to stay in the steel. And that follows that 33 kips have to go somewhere out into the concrete. Okay? So the amount of longitudinal shear that needs to be transferred is 33 kips. So it's sort of common sense. If you don't want to figure it out yourself with ratios, you can use the equations that are provided within the specification. Equations I6.1 is for external force applied to the steel. I6.2 is for external force applied to the concrete only. But again, these are just ratios. So once you determine the longitudinal force to be transferred, you need to determine how it can be transferred between the steel and the concrete. And the specification provides you several different mechanisms to accomplish this transfer. If you take a look at the mechanisms available for both filled and encased sections, you can use direct bearing or shear connection. And for filled sections only, you can use the actual bond strength between the steel and the concrete member. You can use the maximum of these, but you cannot use all of them together. All right? So you have to choose one, but you can use the one that gives you the most resistance. And the whole point is to be able to provide a resistance, a mechanism resistance, that is greater than the longitudinal shear that you have to transfer between the 2. Just as an example of how this might be accomplished, what I mean by a direct bearing mechanism is just to use embedded bearing plates, such as shown on this encased column. In this case, we have 2 sets of bearing plates, and they really behave just like gigantic shear studs. Of course, option 2, shear connection, is to use shear studs and place them within this load introduction length. Now, when we were writing the specification for this different shear stud provisions, what we realized was the specification in 2005 really didn't address this issue very well because it didn't say what strength of anchor to use. The 2005 specification provides shear stud strengths for composite beams, but it didn't really say anything about composite components like this. Also, you wonder what resistance or safety factor is appropriate. The 2005 specification, again, provided safety factors and fee factors for the beam as a system. All right? You applied it to the flexural strength, but you did not apply it to the actual shear stud. So that we left with 2 options here. Your first option was to just tell everyone to use Appendix D. And the second option was to sort of look at all the data, conduct our own study, and to try to provide a simplified method that could be used for just this specific condition with these specific shear studs. So that's what was done. Luis Polaris and Jerry Hajar did this study, and it became the basis for section I-8.3 that we'll discuss in a minute. Our third possible load transfer mechanism is bond, again applicable to fill columns only. 60 psi is the bond strength that's provided. This is actually quite low, and it comes with a fee factor of 0.45, which is the lowest fee factor in the entire specification, representing all the different scatter that's in the data. So you aren't going to get a whole lot of use out of these bond provisions if you have high transfer forces. And then finally we have our detailing provisions. We'll discuss those a little bit later on. That takes us to I-7, composite diaphragms and collector beams. And this is just a pointer to a commentary discussion. Really the commentary gives a little bit of information on composite diaphragms using SDI's diaphragm design guide. And it talks about the use of composite beams as drag struts or collectors. A couple of notes on using composite beams as collectors. First of all, beware of the non-composite composite beam. And what I mean by that is don't just design the beam as if it was a steel-only beam and then add 2 or 3 studs that can transfer the lateral force, because those studs don't know that they're on there just for transferring the lateral force. They are going to try to resist your gravity loads, and if there's that few of them, they will probably fracture. Right? So provide a minimum amount of composite action. I would recommend 50% or so if you're going to use a beam as a drag strut. Secondly, it's generally unnecessary to superimpose your horizontal shears from the gravity loading and the lateral loading. That reason is twofold. First of all, the combinations in AISC 7 give you sort of a break by reducing your live load for all the combinations that have lateral load as well. And then you have this issue of the direction of the shear flow. If you look at the top portion of the beam here, your shear flow starts in the center and emanates outward for gravity loading. But for lateral loading, all of the applied shear is going to be in one direction. So half of the beam is going to start unloading. The other half of the shear studs are going to start overloading. But if you have a minimum amount of composite action, you should have enough ductility left to redistribute that force. So you can check all of the anchors together for just lateral loads. And the final point that the commentary makes is to check the interaction of flexure and axial load. And that interaction is done by just looking at the non-composite axial strength of the member in combination with the composite flexural strength. So it really doesn't have a mechanics-based background, but it's a fairly safe and easy way to handle that situation. Then we move into section I-8, steel anchors. For I-8, the first part of this, we have steel anchors and composite beams. Again, no major changes. I-8.3 are these new provisions for steel anchors in composite components, where we have shear, tension and shear interaction. We really only use the shear portion of these provisions right now within the load transfer region of composite columns. The tension and interaction provisions are there for future provisions as well as for the odd case where you might have a composite wall system that has some of this. But primarily we're just looking at the shear provisions. And the use of the study that we took a look at first was if you have an H over D for your shear stud that is greater than about 5, almost 100% of your anchors fail within the steel shank, within the range of concrete strengths that the specification allows. So what was done in this new section is to say that you were allowed to just look at the strength of the concrete alone as long, or the steel alone, excuse me, as long as the H over D ratio is greater than 5. So you can ignore your concrete limit states. We also looked at all the data to see what phi factor should be used, and the phi factor of 0.65 was determined. This was fortunate in that it's the same phi factor used for studs in ACI 318, but it was corroborated independently. And then the bottom line for this information is the table within the specification provides H over D limits for shear loading, tension loading, and shear plus tension for both normal weight and lightweight concrete. All right, so this moves us to Section I-9, Special Cases, and really all Section I-9 says is that if you do enough testing to satisfy yourself and the building official that everything is okay, then knock yourself out. So that takes us to the end of this Part 1. We're going to take a few minute break here to answer a couple of questions, and then we'll move on to Part 2, the design examples.
Okay, Will, we have a couple questions on the floor right now. The first question is, does the bond strength between the concrete and steel account for prime coating of the concrete, or do we specify no such priming for this condition?
We don't specify any such priming. It was done just based on the raw steel, which sometimes does have your oil film coat on it. So painting of the member probably really wouldn't have much of an effect on the low bond strength. Again, what you're going to see is that the bond strength is so low that you're really going to have to provide some sort of positive means of connection. You're going to have to use steel anchors, embedded plates, or you're going to have to apply the forces to both members concurrently to really be able to achieve the composite action you're looking for, because bond is just so variable. The tests do recognize the fact that the more eccentricity you put on the connection, the more strength you get because of the mechanical interlock. So you actually can develop the full plastic capacity of a filled tube without shear studs and bending. But if you're looking at straight axial compression, you're probably going to need to provide some means of positive transfer.
Okay. Yeah, and just to clarify, he was the person was asking about the prime coating of the steel, and I think I said concrete. I apologize.
Yeah, I understand.
Okay. All right. The next question is, where steel W sections are embedded in a shear wall and used to carry most of the tension in a shear wall at the base, can the load transfer from concrete to steel or steel to concrete be done using angles welded to the steel flanges?
Absolutely. That is using the bearing mechanism that we just discussed, and that's basically instead of using embedded plates like what we were showing there, you're using the angles as an embedded plate. So yes, certainly. You're allowed to use, I believe, 1.7 F'(C) as your bearing strength, which recognizes the increased confinement of the concrete. And I believe the question goes on to ask what the maximum and minimum spacing between the angles would be. If you look in the specification provisions, the detailing provisions for the steel anchors, I would follow a similar provision for steel anchors and composite components with a maximum of about 24 inches between angles.
Okay, and then just one more question. I'm going to jump to slide 51 real quick. When talking about the material and detailing limitations, in this slide you talked about bundling at the corners. Can you just describe what that would look like? I don't know that we can draw that up, but if you could describe how that would happen.
Sure. What I was talking about here is instead of placing the longitudinal rebar along the XX and YY axis like you see here, is just to take those bars and push them out to the corners of the concrete so that all your longitudinal reinforcement is placed within the corners. You can achieve that by either using 4 bars that are large enough to handle the load that you're applying to them, and if that won't do, what I was saying is you could use bundles of 2 to 3 bars that are in the corners. Again, that comes with its own set of issues with increased lap lengths, but it does get the longitudinal reinforcing that is along the axis out of the way of possible steel beam connections that want to come in to the XX and YY axis. So it cleans that up. I see another question that just came up that said we usually design the drags and collector elements as non-composite since the concrete will crack in tension and we no longer have a composite section. We usually use minimum number of studs in these members. Is that correct? If you would like to design drag struts as non-composite members, that is certainly fine. What I'm saying is that you should use at least a number of studs to get you, I recommended 50%, absolute minimum 25% of composite action. So you're certainly welcome to design them as if they aren't there, but at least put enough studs on there to achieve 25 to 50% composite action to allow some reserve capacity and ductility within these stud anchors. Don't just put a few studs on there. So if the minimum number of studs based on your maximum spacing is not getting you to that point, then no, that's not correct. You need to put more than that.
All right. Thank you very much, Will. You want to get going on part 2? I think we can move ahead.
Excellent. All right. Okay, so part 2, talking about the design examples. In putting together this portion of the presentation, I decided that rather than just flipping through slide after slide of numbers and equations, that I would sort of take a behind-the-scenes look to a few specific design examples to give you an idea of some of the decisions that were made within the committee in putting together these design examples. So before we jump into that, I'm going to give sort of a brief layout and scope of the design examples, and then again we'll get into this review of the select design problems. So the question is, why do we update to begin with? And the answer to that is the 2005 design examples were a little all over the place. We had your standard composite beam design, but then we had a filled column in compression, an encased column in compression, an encased column in tension, back to a filled column in tension, a filled column in shear, but no encased column in shear, and then a combined member example for encased, but not for filled. So we sort of hit up on a couple points and missed a couple points. So what we wanted to do is to fill in the gaps and to restore order to the design examples. And that was done by separating them out into different sections. All the beams are now up front, all the concrete filled members are now together, and then all of the encased members are now together at the end. And the shear provisions have been moved to the different combined loading examples, and a new combined loading example has been added, I6, for concrete filled members. All right, the second part is to provide more detailed guidance for the most commonly used composite members, which are beams. Okay, so we've always had this I1 composite beam design, which is a good example that uses the manual tables, but we wanted to put sort of a more explicit design example that went through a lot of hand calculations. So we added I2 composite girder design to give that type of an example. And then the third reason for the update is to cover the new provisions for the 2010 specification. I've been talking about that for almost an hour now. So we had to add sections I3 and I8 on load transfer, I7 for non-compact and slender elements of a box column, and I12 to handle these new steel anchor and composite component provisions. These design examples are available right now at AISC.org/design examples. They are free. You do not have to buy anything. They are there for you to use. This has not only the design examples from the 14th edition manual, but also has the design examples from the 13th edition manual. So feel free to download those anytime you wish. So the two different problems we're going to take a look at are first in depth, this composite girder problem, and then we're just going to briefly touch on I8, an encased member for force allocation and transfer. So the problem statement for the girder design problem is a 30 by 45 foot base. The girder is supporting beams at its third points. We have a 7.5 inch thick slab with 3 inches composite deck, normal weight concrete, and the live load is 100 pounds a square foot, and the problem just says design the most economical girder. So there are a couple steps for composite beam design. Step 1, determine the loads. That doesn't have anything to do with composite design. That's what you always do. And then we have steps 2 and 3 for checking the flexural and deflection limits on a non-composite section prior to the concrete hardening. And then steps 4 and 5 to check those same limits on the composite section. Now again, the section that we're looking at is an unshored section. So step 1, determining the loads. First of all, you might be wondering why we used a 7.5 inch thick slab, and the reason is for fire rating. We wanted a 2-hour rating without having to spray fireproof the deck. UL rating requires that you use either 4.5 inches of normal weight concrete or 3¼ inches of lightweight concrete above the top of the deck. So with our 3-inch deck, normal weight concrete, we ended up with 7.5 inches. And you can get tables like these at the back of most any deck manufacturer's catalog. So as far as the weight of this, from a deck catalog, it's about 75 pounds a square foot. But you also need to be cognizant of this issue of concrete ponding. If you're placing concrete, the beams are going to deflect. The girders are going to deflect. You're going to get some small deflections within the deck. And if you tell the contractor to pour the slab up to a certain elevation, there are going to be sections that are thicker than your nominal thickness. All right, so you need to apply a little extra load in order to handle this concrete ponding issue. So the question is how much? Well, AISC Design Guide 3 recommends that you use about 10% of the slab weight extra. So for a 75 pound a square foot slab, you'd be adding 7 to 8 pounds a square foot additional. The other way to handle this same issue is to pour the slab to a constant thickness, which is a little more difficult, and you'll have to discuss with the owner whether they're okay with their slab waving up and down, but it is certainly possible. In this design example, what we did was say we were going to pour it to a constant thickness just so that we could ignore this extra ponding weight for the purposes of an example. Then you get to your construction live loading. A lot of people use 20 pounds a square foot. It's been around for a good while. What we did with the design example is to use ASCE 37, which is design loads on structures during construction. And they recommend where concrete is going to be transported and placed by hose, as is fairly common in these type of structures, that you use a live load of 25 pounds a square foot. So 25 pounds a square foot construction live load was used. So once you determine your loading, you then go on to steps 2 and 3, your flexural strength and deflection limits of the non-composite member. Now the big question for checking the non-composite flexural strength is, does the deck brace the beam. And for the case where the deck runs perpendicular to the beam, such as the deep beam on this slide, I think most engineers would say the answer to that question is yes, it does brace the beam. And you would be correct. If you actually want to put some numbers to this, Todd Helwig and Joe Ura put out some articles in the Journal of Structural Engineering that gave equations for calculating the bracing effect of the shear diaphragms on beams. When you run through the equations they provided for most standard rolled shapes in typical beam layouts, you'll definitely get a full bracing capacity. If you do have a very deep, slender web with only a few beams, perhaps a footbridge type situation, you might want to dig into this a little more to make sure that you're okay. But that's sort of the easy question. The harder question is, what about when the deck is parallel to the girder? A lot of engineers are concerned that the deck might sort of bunch up in an accordion-style failure in this condition and not provide the bracing that's needed. So I talked to a good number of very smart people in terms of stability and deck design, and the overwhelming answer that I got to this question is maybe. Not too helpful an answer, and this is the reason why it's maybe. If you have a metal deck that is attached to your girder and all four sides around the bay next to that girder so that it forms a diaphragm, then the answer is almost certainly yes, it will brace the girder because it's acting as a diaphragm. All right? If you look up the shear strength of a metal deck in a deck catalog, it doesn't give you the shear strength depending on the direction of the deck. It's just the shear strength. It doesn't give you stiffnesses depending on the direction. It's just the stiffness of the diaphragm. So if it's properly attached on all sides, it'll act as a diaphragm and brace the girder. But if it's not attached properly on all sides, or if you have, for instance, deck fillers, fillers between the edge of the deck and the girder, no testing has really been performed on a situation like this, so we can't positively say that that parallel deck with that kind of condition is going to brace it. So it's probably a good idea to assume that the distance between purlins or filler beams is your unbraced length. It really won't affect your design a whole lot, so that's what was done in the design example. All right, next, non-composite deflection limits. For non-composite deflection limits, L over 360 or 1 inch is what AISC Design Guide 3 recommends. If you can't meet that, you need to either get a bigger section or you can use cambering. If you're going to camber your beam, there's a couple of limitations to be aware of. You probably only want to camber out 80% of the pre-composite dead load. This is just realizing the fact that your simple connections on the end really aren't so simple. They do provide some amount of stiffness. Reduce it to the nearest 1/4 of an inch with a 3/4 of an inch minimum. And be very careful with your steel anchor cover. The reason I say that, there was a change between the 2005 and 2010 specification. In 2005, we said the second part of this sentence, that there shall be at least a 1/2 inch of concrete cover above the top of the installed studs. A lot of engineers took this to mean that if you poured the concrete and there was only 3/8 of an inch cover over the top, that it was unacceptable and you would either have to accept it on your own or get the contractor to tear it out. That really wasn't the intent. So in 2010, it was changed to say that there shall be at least a 1/2 inch of specified concrete cover above the top of the steel-headed stud anchors. All right? So if it does come out to be 3/8 of an inch, it's okay. It's not a strength issue. You just don't want them actually sticking up through the slab. Right? You have to have some common sense with this. You also need to pay attention to the first part of this sentence, which says that the steel-headed stud anchors after installation shall extend not less than 1.5 inches above the top of the steel deck. So the key here is after installation. When you take a look at the length of a steel anchor, it's actually reduced a little bit when you weld it down to the base metal, and that's called burn-off length. So standard burn-off lengths, if you're welding the stud directly to the steel, is about 3/16 of an inch. But if you're welding it through deck, it's more like 3/8 of an inch. So pay a little bit of attention when you are coming up with the length of your studs to take into account this 3/8 burn-off value. The next step is to check the composite flexural strength. And there are several different methods for checking the composite flexural strength within the specification. Method 1 is to just use the manual tables. Method 2 is to use direct calculation with the Chapter I specifications. And then method 3, which is probably the most common method, is to push the little go button in RAM, RISA, etc. This is not a AISC sanctioned method, but it does happen to be the most popular one. We'll leave that one to you and take a quick look at methods 1 and 2. Method 1 is simply using the tables within the manual. The first example goes through this rather explicitly, so I'm not going to spend any time on it. We're going to take a look at method 2, which is direct calculation with Chapter I. And really this is just the use of statics. And this comes into play when you're trying to do something by hand, and maybe something a little unusual. I was doing a little spring cleaning earlier this year for my calculations, and I ran upon this little gem where apparently I was trying to calculate the composite strength of a beam that already had a cover plate, that I was putting on a new cover plate and some other angles. I don't recommend this. This probably wasn't a good idea to begin with, but it just goes to show that it is possible if you really need to do something. So the first thing you need to know when doing this by hand is exactly what composite percentage means. And your composite percentage is just the sum of your anchor strengths from the end of the beam to the point of maximum moment, sum of Q sub n, divided by the minimum of either the yielding of the section or the crushing of the concrete. So if your sum of Qn equals steel yielding or concrete crushing, then you have a 100% composite member. If it's less than that, you have a partially composite member. And the question comes up a good bit in the Steel Solutions Center of how much less is okay? What's the minimum? And the answer to that is there is no minimum within the actual specification. But most of the design aids and software that you'll see is limited to 25%. And the commentary actually recommends more like 50% as a minimum. In fact, there's a lot of what I call scary words within the commentary, where they say that less than 50% composite action requires large rotations and can result in very limited ductility and probably the scariest, premature departure from elastic behavior. All right? So there are a lot of beams out there with 25% composite action. They work fine. But if you have your choice in new construction, I would highly recommend you go with more like 40% as a minimum. And the reason I say this is looking at this chart, which has the composite percentage as a ratio on the bottom axis. So 1.0 on the x-axis here is fully composite. And then the ratio of your beam strength to the fully composite strength on the y-axis. So if I take a look at 40% composite action and I go up and over, I'm getting close to 80% of the full composite strength of that beam already. Right? Anything more than that, your studs really aren't doing a whole lot. You're adding a lot of studs for not much return. Anything less than that, though, you see that the curve here is pretty steep. So you're pushing your studs harder and harder, and you're getting less reserve ductility. So in new construction, 40 to 50%, good way to go. So once you know what that is, step one is to determine your concrete compressive force, which is the minimum of the yielding concrete crushing, or in a partial composite beam, sum of Qn. And then you go to our old friend statics. You calculate the plastic neutral axis by summing forces in the x direction to determine where the force above and below the P and A is, so you can find your plastic neutral axis. And then, as generally happens, every time you sum forces, you follow it up with summing moments. So the nominal flexural strength of a composite member is just the sum of the moments about, in this case, the concrete or the steel flange force. It really doesn't matter. You can sum moments about anywhere, and you're going to get the same answer as long as there's not an external applied axial load. We've made this even easier for you in that the commentary figures that we added back sort of goes through how to handle each of these situations and comes up with the moment arms to use for you. So that takes us to the last step, which is to check our composite deflection limits. The limits in AISC Design Guide 3, you use either L/360 or 1 inch for live loads. It does allow a 50% reduction in design live load. However, IBC 2009 requires you to use L/360 with the full 100% design live load. So be careful there. So the main question here is what moment of inertia should be used? And we're going to take a look at that by sort of taking a trip down memory lane and seeing what has been used in the past. And we're going to start out with what I call the steel blankie. And that is the manual that makes everybody feel happy and warm inside. And that happens to be the 9th edition ASD. This thing is over 20 years old, but people still love it. So that manual said to use an I effective equal to the I of the steel section plus a ratio of partial composite action to the transform moment of inertia. And then if you move from this up to your 3rd edition LRFD manual, the equation in the top right here you'll see is the exact same. So it didn't change, just some of the terms changed, but it was the same equation. But we added this sentence that says for realistic deflection calculations, so I guess previously it was unrealistic, I effective should be taken as 0.8 I effective or 0.75 I effective. So you were trying to multiply I effective by itself, and they gave you the choice of using 0.8 or 0.75. It was a bit confusing. They also gave you an alternative to use this new I lower bound equation. So moving into the 13th edition manual, tried to fix this by saying that I effective should definitively be taken as 0.75 I equivalent. And the I effective equation was given as shown here. All right? That wasn't supposed to say I effective. That was supposed to say I equivalent. Right? So it was supposed to say use 0.75 times this I equivalent equation. That was actually fixed within an errata to the manual. All right, so we finally got our act together in the 14th edition manual, where we now definitively say you can either use I lower bound or I effective should be 0.75 times I equivalent given here. All right, so that's sort of the winding path we've taken to get to where we are right now. But you'll notice I haven't answered the question. And the reason is because when you ask which method is correct, the answer is really neither of them are perfect. If you look at raw test data for composite beams, it appears that the I lower bound equation is a pretty good fit. But mechanics-wise, it doesn't make any sense. You're using a plastic model equation for a serviceability elastic deflection issue. But it does appear to match the data. However, this is commentary, so you are allowed to use whichever method you wish. What the design examples decided to do is to compare both methods and to take the higher moment of inertia, since they're both allowable methods. Again, this is the subject of some ongoing research. You might want to see what your software is doing and decide as an office exactly how you want to approach this particular question. Okay, so that takes us through I2. And we've got just a few minutes left to get through section or problem I8 on encased member force allocation transfer. For those of you who don't remember, an hour ago, force allocation and load transfer, you have a column, you apply some force to it, that force has to get transferred out to the concrete or vice versa in order to use the section as composite. So the problem statement here, we had an encased composite column, and we were looking at external force applied to the steel only, the concrete only, or both materials concurrently. For force applied to the steel only, you were looking at a situation such as what I looked at earlier, where you have all the force coming down a steel column into a composite column. So what we did here is calculated the longitudinal shear first. So you needed the ultimate required strength, which was 1,560 kips. And then you're going to look at the allocation based on a plastic strength model. We've talked about this previously. Your section strength is 3,400 kips, and the steel portion of this is 665 kips. The concrete portion is 2,700. So you can take this information and go into specification equation I61, which sort of gives you this ratio of how to determine your longitudinal shears. Now, if you recall previously, we sort of did this with common sense. We just looked at it. And you can actually back common sense out of the specification equation. So if you back P sub NO out, your equation looks like this, and then you substitute the word for the variable game. In this case, this equation is simply equal to member strength minus steel-only strength over member strength, which is equal to concrete strength over member strength. So you're back to common sense. It's just a ratio. If you run through those numbers, you will come up with a longitudinal shear requirement of about 1,200 kips for load applied to the steel only. You can do the same thing for load applied to the concrete only with specification equation I6-2, except in this case it's a ratio of steel strength to member strength. And this is down to a longitudinal shear of only 300 kips. And then you have to decide how to transfer this. If you'll recall previously, all the different mechanisms for force transfer, either direct bearing, shear connection, or bond for filled sections. This is an encased section, so we have to look at either just direct bearing or just shear connection. For direct bearing, we use these embedded bearing plates within the design example. And the real question here is how to design the thickness of those bearing plates. You can either look at them as, let's say, simply supported beams spanning between the flanges. That's a fairly conservative option. If you have way too much time on your hands, you can go into finite element modeling, such as shown here. What we did in the design example is to use yield line theory. And yield line theory is sort of like steel voodoo. You sort of draw some lines out and you can come up with a capacity equation for a connection design like this. It's actually behind a good number of the equations in Chapter J of the specification. So I highly recommend taking a look at that method. So we provide those equations within the design example. The second possibility is to use shear connection with steel-headed stud anchors. And when you're going to use the steel-headed stud anchors in this situation, you're going to be using those new provisions that we discussed earlier, where you have to have a certain H/D ratio for your steel anchor. In this case, we have normal weight concrete. We're in shear only, so you have to have an H/D of the stud of 5, and then you can use the base steel strength of the stud without looking at the concrete. Now, a couple of notes on this. When you're doing this, the H/D ratios and head geometries, spacing limitations, etc. in the specification preclude concrete pry-out in shear. What they do not preclude is concrete breakout toward a free edge. This is normally not a problem with composite columns because you have a foundation at one end. There's really not a free edge in that direction. But the commentary also warns against the possibility of edges parallel to the line of force breaking out. So what I mean by that is sort of shown in this slide, in that it's actually possible, if you apply enough force to the steel section, to blow out a portion of the concrete next to it. Now, this really isn't a realistic limit state. I've never seen it happen in a test. There's generally a lot of transverse reinforcing ties that go through this to prevent it from blowing out. But if you really do want to put some numbers to it, it is possible using ACI 318 Appendix D. For those of you who have not had the pleasure of using ACI 318 Appendix D, if yield line theory is steel voodoo, then this is sort of like double secret concrete voodoo. If you actually look and stare at these little psi factors long enough, you can actually see the voodoo coming out of it. It's complicated, it's not very fun to work through, but it is possible. All right? So if you go through all these equations, and it's shown within the design example, what you determine is that this limit state really is not very applicable, so you're okay. One sort of last topic to touch on is the topic of load introduction length, which is how quickly you need to transfer these shears. In 2005, we said that the shear connection shall be distributed along the length of a member at least a distance of 2.5 times the depth of the encased composite column. In 2010, this was changed to say that the anchors shall be distributed within the load introduction length, which shall not exceed a distance of 2 times the minimum transverse dimension of the column. Now, for those of you who are still paying close attention, these basically said exactly the opposite of one another. 2005, not so good. 2010 is really what the intent was. The intent is to try to get the section into equilibrium as quickly as possible. We really want to get that column to be acting composite very fast. So what we're talking about here is if your load transfer region is the depth of the connection coming in, then your load introduction length is twice the width of the column above, all the way down to twice the width of the column below the load transfer region. So all the shear studs that need to be placed within this zone. Now this can become sort of a problem, such as the situation I had. If you take a look at a high-rise coming down into a concrete building, the specification would say that you need to put all of the load transfer studs within this teeny little red zone here. If that's not feasible, what you can do is you can use a what I would call an extended load transfer length, and that's just to take the entire lift, the entire floor, from, in this case, level 3 to level 4, as shown in this larger red zone. Take that as your load transfer length, but then you cannot design that lift as composite. So you just take another floor of non-composite design, transfer all the force required, and then from then onwards, from level 3 downwards, you can design those columns as composite, as shown here in the blue. Okay, so that sort of concludes the points I want to hit on for that example. So as sort of a summary, the 2010 specification and design examples have been greatly expanded and reorganized for ease of use. Mainly we've done revisions to the reinforcing detailing through reference to ACI 318. We've added new local buckling provisions for concrete-filled tubes to allow non-compact and slender members. Load transfer provisions have been clarified. The shear provisions have been consolidated into one new section. We've added a new section on composite collector beams and diaphragms, and we've added a new section on steel anchors with new information on steel anchors in composite components for load transfer provisions. The design examples now provide problems for each different member type for each different force action: compression, tension, shear, and combine. So again, greatly expanded design examples. The 2010 specification is freely available at AISC.org. The 14th edition manual may be purchased either in hard copy or digital form, again at AISC.org. And these design examples are currently available for free at AISC.org/design examples. And that takes us to the end of the presentation. I certainly appreciate your attendance today, and I'll be happy to answer any questions that we might have to conclude the presentation. Thank you very much. Brent?
Will, looks like we have a question. You want to address that?
Yeah, a question on fire rating for composite columns. Encased composite columns are handled explicitly within the IBC 2009, table, I believe, 721. There are actual formulas for determining the fire rating for encased composite columns. And for filled composite columns, AISC Design Guide 19 for fire resistance, as well as ASCE 29, which is the standard calculation methods for structural fire protection, has specific equations for determining the fire resistance of filled concrete columns. So you can get some advantage there and calculate that that fire resistance directly with those equations.
Okay. And then we have another question. In an encased condition with the shear transfer using steel angles, can the concrete be assumed to brace the outstanding leg of the steel angle?
If I understand the question correctly, they're asking whether you would have to take a look at the outstanding angle and bending, or if you can just assume that it's shearing it straight through. I would most likely take the conservative route in that condition and assume that the concrete might not be fully consolidated above the angle, and go ahead and check that outstanding leg and bending. So that would just be my personal take on it.
Okay. And then we have a headed stud question regarding minimum cover.
Mm-hmm.
If the designer specified a cover over the head of the steel anchor, but in place the stud is flush
that
with the top of concrete, is that okay?
Right. That gets sort of into what I talked about earlier with the specified versus what actually happened. For the strength of the anchor, most likely that's fine. If it's got even just a little bit of cover on that, you're probably going to get enough shear strength out of that stud. What you don't want is it actually protruding above the top of the slab. But you really shouldn't even run into this situation. You shouldn't go into your composite beam design with only this minimum half-inch cover above the top of the stud specified. You should go in with more than that, understanding that there are going to be issues with concrete placement, with camber coming out, different issues like that. So you want to give yourselves a little leeway. But just from a pure strength perspective, there shouldn't be an issue with studs, even if they're pretty close to flush with the top of the slab.